Hi everyone. So this is gonna be the next video clip for solving the example problems. I think I am gonna record two separate video clips. First one will cover examples 9-1 and 2, and the second part on the 9-1, 2, and 6 for the first video, and the second video will cover 9-8 and 9. That's my plan. All right, so let's look at the problem. I'm gonna, this time I'm gonna use a whiteboard instead of having my note. So let's see, and this is the first time using this tablet, so let's see how it works. Okay, so hopefully you can see this one. All right, so this is example, oops. Okay, so let's see. Example 9-1. All right, so the question is this. Is the compact and laterally braced section shown in this figure 9.2 sufficiently strong to support the given load if Fy is equal to 50 KSI? So I'm going to draw a figure here. So here we have a beam, simply supported. And based on the description, I just said that it is a compact section and then laterally braced section, which means L sub B, the unbraced length is going to be 0. So in the lateral direction, everything is kind of braced. So we don't need to worry about the lateral torsional buckling. Okay. And it is a compact section. And the length of the beam is 21 feet. And we do have a load, of course, on top of this beam. And we have two different kinds of loading here. The dead load is 1 kip per unit length feet. It doesn't include beam weight. And the live load L is going to be 3 kips per feet. Okay, so okay, and the given section is this W 21 by 44. So 21 by 44. And as I said, this dead load doesn't include, so not including the beam weight. Okay, so how can we determine whether this beam, the 21 by 44 section, if this beam is compact and laterally supported beam with this span and this given load, whether this is, good enough to support the load or not? And one more thing, the Fy is given as 50 in KSI. Okay, so the first one, we have to find out the maximum moment due to the load. Okay, since this dead load, the 1 kip per feet, doesn't include the beam weight, I'm gonna include the beam weight, which is 44, right? So it is 44 pounds per unit length feet. So our dead load, so intensity of this uniform distributed load, including both dead load and live load, is now equal to 1.2 times that plus 1.6 times L. So I'm going to use 1.2 D, 1.6 L. This is for, by the way, LRFD method. And I'm going to solve the problem using LRFD method and ASC method. The solution is available in the textbook, so you can go over it. So WU is going to be 1.2 times the dead load, which is 1 kip. And then we're going to add this 44 pounds. So when I convert it into the kips, it's going to be 0.044. So when you multiply by 1,000, it's going to be 44. So this is going to be dead load times 1.2, and then 1.6 times L, which is 3. So WU, the intensity, the factored intensity is going to be 6.05. kips per feet. Okay, so that is going to be WU, the factored intensity. So how can we find out the maximum moment? When we have a uniform distributed load, the bending moment diagram, if you may remember that, the shear force diagram looks like this, so that we will have a quadratic function, and the maximum bending moment is going to be located in the middle, and that mu, the equation is going to be WL squared over 8. So in this case, W is going to be 6.05. L squared, L is going to be 21 feet. So I'm going to convert everything. I did not convert it feet in inches at this moment. So I just use a 21 and divided by 8. Then the value is going to be in kip and feet, right? So, and it should be squared. The WL squared over 8, yep. So when I calculated, I got 333.5, 333.5 in kip fit. So this is going to be the maximum moment that we have to support due to this given loading. So that's the first step. We have to come up with the maximum moment. And then this is, by the way, the factored moment. So it is going to be now our demand using the LRFD. So we always satisfy this capacity should be larger than or equal to demand. And this is going to be our demand, factored demand. And the capacity is going to be phi times mn. In this case, I said the unsupported length is going to be 0. So mn is going to be equal to mp, right? So phi times mp is going to be our capacity, right? So if I can show that this phi times mp, the capacity, is larger or equal to this 333.5 kip fit, then this section is good to support this load. So what is mn, which is mp in this case? Mp for the maximum plastic moment is going to be Fy times Z, right? And Fy is 50 ksi. What is Z? Z value is available in the manual for W21 by 44. So when you look up the Z value, I got 95.4 from the manual, 95.4 inch cubic. The unit for the Z is inch cubic. So what if we calculate MP? That is equal to Fy 50 in KSI, and then we have 95.3 inch cubic. So it will give kip an inch unit, right? So here we have a kips per inch square, and here we have inch cubic. So it is going to be, the unit is going to be kip inch. If I'd like to convert it into kip feet so that I can compare it to this 333.5, I have to divide it by 12 to convert the unit from kip inch to kip feet. So when I calculate this number, I got 395.7. 7.5 in kip feet. Is this all? No, because this is the entire MP, and we have to have a factored MP. We have to multiply by phi factor, which is 0.9. So phi MP is going to be 0.9 times 397.5. That is 358 kip feet, which is larger than 333.5 kip feet, the factor demand, right? So the answer is yes. Our section is good and solid and strong enough to hold this load based on the given load. So that is example 9-1. Okay. Now let's go on to example 9-2. Example 9-2 is pretty similar problem, but now this is a design problem. So we're going to design the beam based on the given loading. So the difference between 9-1 and 2, 9-1 with a given section W21 by 44. So we just check the capacity based on the section properties and the material property and compared to the factor demand. Now 9-2, the question is this: select the beam section by using both methods. I'm going to focus on, in this case, I'm going to use ASD. For the span and the loading shown in this figure, assuming the full lateral support is provided for the compression flange by the floor slab above, which means the L sub B is equal to 0 as well, and Fy is equal to 50 KSI. So I'm going to draw a case here. So here we have a simply supported beam, and the loading is, we have uniformly distributed load, and then we do have one concentrated force right in the middle. So this P, this is PL, the live load, it's 30 kips, and this uniform distributed load, it is only for the dead load. So WD is 1.5 kips per feet. So this is the intensity of the dead load. The span length is going to be 30 feet, and the live load was applied right in the middle. So this is going to be 15 feet and 15 feet. Okay. And Fy is equal to 50 KSI. And L sub B, I said, is equal to 0, which means there are lateral support, and this beam is supported by the floor on top of that, the slab on top of it. So we do not need to worry about the lateral flange, lateral torsional buckling as well. So I'm going to use ASD method in this case. All right. So the first step is going to be this. This is the design problem again, but again, we have to include the self-weight of the beam, right? But in this case, until we select the section, we do not know the beam weight. So the first step is going to be the estimation of the beam weight. All right. So let's start with that. So W, in this case, WA for ASD. And this WA doesn't include the self-weight because we do not know the self-weight yet. So based on the given information, WA is going to be 1.5 kip per feet, right? And then PL, so I would say this is going to be PA is equal to 30 kips. By the way, this PA is coming from PL. For ASD method, we just add dead load and live load without having any factor. That's why PA is equal to, just directly equal to PL. For LRFD, we use WU and PU. These are all factored quantities for LRFD. So WU, because WU is coming from the dead load, WU is going to be 1.2 times 1.5, and PU is going to be, this is coming from the live load, so it's going to be 1.6 times 30. Okay, so that's the difference between LRFD and ASD. So let me go back to ASD. So this is my WA and this is my PA. So what I'm going to do, I'd like to find out the moment due to these two different loading. The first one due to the uniform distributed load. The other one, PA, that's the concentrated force. So the maximum moment, which is going to be MA in this case, I'm going to write down here. So first we calculated using the distributed load, which is WL square over 8. So W is going to be 1.5 in kip and feet unit, right? And L is going to be entire length, which is 30 square over 8. So this is going to be the maximum moment right in the middle, and that is the location to have the maximum moment. And due to this concentrated force as well, and due to the concentrated force, the maximum moment in the middle is going to be PL over 4. you can, if you don't need to memorize this, you can easily think about the bending moment diagram. So this is kind of a side note, but here we have a simply supported beam. We already covered it in the structure analysis. Due to the bending, the uniform distributed load, the bending moment, the corresponding bending moment is going to be the quadratic function because the load is uniform. The shear is going to be linear function, so the bending moment is going to be quadratic, and the maximum in the right in the middle, that's the WL square over 8, which is coming from actually. Think about the shear force diagram. It's going to be triangular shape. So the change in moment up to this point is going to be the area of this triangle, right? So 1/2 times the base, which is L over 2, times the height, that is the P. So let's say this is W, and the reaction here is going to be WL over 2, right? So this height is going to be WL over 2, the base is L over 2, and using the triangle area equation, 1/2 times L over 2 times WL over 2, that will give us WL square over 8. When you have a simply supported beam with one concentrated force P, then you're it's going to be P over 2, the reactions. So your shear force diagram looks something like this, and your bending moment diagram is going to be triangular shaped, the linear function. So the value here is going to be the area of this rectangle, which is L over 2 times P over 2, which is PL over 4. So that's what I'm using here. So P is going to be 30, L 30 over 4. Okay, so when you calculate the maximum moment in the middle, I got 393.8, 393.8 kip feet. So this is going to be my demand using AST. Again, there's no factors. That's why I just use the original values and find out the maximum moment. 393.8 is going to be our target demand. So what we're going to do, I said this is the first step to estimate the beam's weight. So, and again, this dead load doesn't include the beam weight yet. So based on the given dead load and the live load, this is the maximum target moment without including the beam's weight. I'm going to go to table 3-2 to see which size of the beam will meet this criteria. Okay, so from table 3-2, I pick, so you have to compare the MP over omega value because else B was equal to 0, right? Here. So we can fully maximize the capacity of this beam against the bending. So compare this value, MP over omega for AST, and select the section, which is W21 by 68. W21 by 68, which the corresponding capacity, the factor capacity is 399 kip fit, which is larger than our target preliminary target demand, 393.8. So this is the first step to select the beam based on the given load. And then now, since we pre-select the beam, so now we have information about the weight, right? So we're gonna add this weight onto the given dead load and live load to calculate and modify and update our bending moment again. So to do that, now WA is equal to 1.5 plus 0.068 now. It's going to be 1.568. Unit is kip per feet. And PA is still the same, 30 kips, because there's no difference. So we can update our MA calculation. MA now is equal to 1.568 times 30 square over 8 plus 30 the load and 30 the length divided by 4 I got 401.4 kips. Okay. So earlier, I pre-selected 21 by 68 based on the given load, dead load, and live load. And the corresponding capacity was 399 kip feet. Now, if this is a good enough section to support all the load, including the self-weight, the corresponding capacity should be larger than the demand. Now, when we update the demand, including the beam's weight, which is 68 pound per feet, now our target demand is increased from 393.8 to 401.4, which is larger than 399. So that means this beam is not qualified to be selected our candidate, right? So we have to go to the table again, table 3-2, and then look up MP over omega value to meet the criteria. So this is our now demand. Find out the section which has a larger capacity than this, which is W24 by 68, and the corresponding capacity value is 442 kip feet, which is larger than our demand. Okay, so this is gonna be our final answer. So that's how we can solve the problem. I think I'm gonna stop here for this video and then continue to solve later examples in the other video. All right, thank you.